All right, so today we're going to start talking about co-state estimation using pseudospectral methods. So in order to do this, we're going to go back to the simplified form of the optimal control problem. So if you recall, the simplified Mayer form optimal control problem it looks like this. We want to minimize phi, which is a function of x of plus 1, subject to the dynamic constraints dx d tau, which we abbreviate by x dot, equals f of x of t, or x of tau, and u of tau. And then we have an initial condition that x of minus 1 equals x0, and tau is on the interval -1 to plus 1. So that was the problem that we had described, that we had formulated previously, and we were doing all of our development of the pseudospectral methods with that formulation. Now, given this, in order to do co-state estimation, remember we need to introduce this concept of the co-state into the problem. So what we do is we first look at the formulation of the optimal control problem using one of these pseudospectral schemes. So if you remember correctly, what we had was from the calculus of variations. I'm not going to derive these from the calculus of variations. We obtain the following system. We get that lambda dot, well, we can do it in whatever order. Lambda at plus 1, which is the co-state at plus 1, is equal to the partial of phi with respect to x at plus 1. If you remember that from the formulation that we had earlier. And basically, we're going to abbreviate this because it's just going to get really hard to write this in terms of the partial derivative. So I'm just going to abbreviate that as the gradient with respect to x of phi, and again of x plus 1. So now, that's the first optimality condition. Second optimality condition is lambda dot is equal to minus dh dx, right? Which in this case is just going to equal minus the gradient with respect to x of lambda, of the inner product of lambda with f. So this notation here, when I use this, it means inner product of lambda with f. And you'll see in a bit that it'll actually make life easier when we actually write it that way. And then finally, we wind up with the condition that dh du, or the partial of h with respect to u, has to equal 0. And this we abbreviate as the gradient with respect to u of h, where h, in this case, is just equal to lambda transpose f, because we don't have a Lagrange cost in the problem. So these are the optimality conditions that come out of from the continuous time optimal control problem. So now what we're going to do is we're going to try to make a relationship between what you get in this continuous problem to what you get in the discrete problem when you actually discretize using one of these pseudospectral methods. And the way I'm going to start is I'm going to start with the Gauss pseudospectral method. So, and then we're going to do co-state estimation using Gauss, and then later on, after today's lecture, we'll talk about Radau, all right? And then we'll go on to Lobato. So let's start with Gauss. So co-state estimation using collocation at LG points. So in order to maintain some continuity with the discussions that we had last week, you remember that in the LG pseudospectral method, we start off with a problem where we have this time domain, which goes from -1 to +1, And we have the collocation taking place at these Gauss points, which are on the interval of -1 to 1, but don't include either of the endpoints. So we define tau 0 to be -1. We define tau n plus 1 to equal +1. And then these points in here are the LG points. And they are tau 1 to tau n. And tau 1 is greater than -1, and tau n is less than +1. And then what we did was we said, well, we're going to approximate the state using a basis of Lagrange polynomial. So I've got the state approximation. So I say the state is going to be approximated by this function capital X of tau, which is the sum from I equals 0 up to n of xi times Li of tau, where this Lagrange basis, Li of tau, is the product from j equals 0 up to n. J is not equal to I, and it's tau minus tau j, all divided by tau I minus tau j. Now, given that, what we did was we computed the derivative of that approximation, and then we collocated that derivative at the LG points. So if I take the derivative x dot of tau, right, this is equal to the sum from I equals 0 up to n of xi Li dot of tau. And then we collocated this derivative, x dot, we collocated it at each of the LG points, j equals 1 up to n. Right? Now, if you look at that, you see that what that leads to, and we've done this before, but I'm doing it again so we can go through the math formally and understand all this stuff. So if we put this in here, what we get is we get the sum from I equals 0 up to n of xi Li dot of tau j is equal to f of xj uj. And again, this is j equals 1 up to n, right? Now, when we put this all together, this matrix Li dot of tau j, these coefficients, becomes the differentiation matrix. So when we write this all in derivative form, because I'm assuming, again, that all of the quantities in here are row vectors, we get the system that looks like this. We get this D matrix times x going from 0 up to n is equal to f going from 1 to n. And you remember that in the Gauss pseudospectral method, this matrix D is an element of Rn by n plus 1. It has one more column than it has rows. This matrix X is a series of rows that start at x0 and go all the way to xn. This is the evaluation of the right-hand side at the Gauss points, right? So we were missing one point in all of this. So what we did was we estimated by quadrature the state at the final point. So we get xn plus 1 is equal to x0 plus w transpose times f1 through n. And this is estimate of x at plus 1 using LG quadrature. Okay. So now we have the stage set to be able to do the rest of this, which is that when you look at this problem, when you discretize using the Gauss pseudospectral method, the NLP that comes out of the Gauss pseudospectral method is as follows. So we've got the Legendre-Gauss method NLP, which says minimize phi of x n plus 1, and it's subject to the following constraints. So you see that there are a bunch of constraints in here. That's the first set of constraints. I'm going to write it like this. F1 colon n minus d x0 through n equals 0. And then we get this other constraint, which is that we get w transpose f1 colon n. I'm just going to put everything to the other side. And that is plus or minus x n plus 1 plus x0 is equal to 0, right? And we also have the constraint that x0 is equal to x naught, which is the given condition. So this is the NLP. I want to minimize that cost function subject to all of these constraints. So in order to be able to compute an estimate for the costate, what we need to do is we need to figure out the relationship between the Lagrange multipliers of that NLP and the costates of the optimal control problem. So the way it works is as follows. First, let's form the Lagrangian of this NLP. So if we write the Lagrangian down, what we get is this, is we got the Lagrangian. Now this is the Lagrangian of the NLP. It's not the Lagrangian of the optimal control problem. So I'm going to denote it with a different letter. I'm going to call it script L. So script L is, in general, it's going to equal the objective function plus the sum of all the multipliers by the constraints. So if we write this down in sort of in an explicit way, we've got, that's the objective function, and then we've got plus. Now what we have to do is we have to append the constraints to the problem. So I'm going to use an inner product here. Lambda, and this is going to be f 1 through n minus d x0 colon n. That's the first part. And then there's another part which has a Lagrange multiplier. I'm going to call it lambda n plus 1. And this is going to be multiplied by w transpose f 1 through n plus x0 minus xn plus 1. And I've eliminated from this problem the initial state because it's fixed, right? So I don't need to have it as a variable in the NLP. And the meaning of all these things is that lambda 1 through n is a matrix. It looks similar to the state at 1 through n. It's lambda 1 all the way up to lambda n. And these are equal to the Lagrange multipliers of the collocation equations. So remember that I have a series of collocation equations because I'm collocating at the n Gauss points. So these are the collocation equations. And each one of those equations has a Lagrange multiplier associated with it, each row. So that's the Lagrange multiplier matrix for that. Lambda n plus 1 is equal to, well, let's line this up. It's equal to the Lagrange multiplier of the quadrature equation. So if you look at the quadrature constraint or quadrature equation, it's here. I have a Lagrange multiplier associated with that. So now what I'm going to do is we're going to differentiate with respect to all the variables in this problem to get the first order optimality conditions of this NLP. So what are we differentiating with respect to? Well, we have the initial state, we've got the state at the Gauss points plus the final state. But remember, I've taken that initial state out. Well, not that I have to take it out, but I can either leave it in there or not leave it in there. If I substitute it in, it just becomes a constant in this formulation right here. So you don't have to differentiate with respect to it. But what you get when you're all done is as follows: is that if you differentiate L with respect to x1 all the way up to xn plus 1 and u1 all the way up to un, we obtain the following, what they're commonly called as the Karush-Kuhn-Tucker optimality conditions of the LG NLP, which is as follows. Because if I take the derivative with respect to all these, I'm going to write this result down because this just requires a lot of algebraic manipulation to get there. I get d 1 through n transpose times lambda 1 through n is equal to the gradient with respect to capital X. Now remember, I'm taking the derivatives here with respect to the discrete variables. I'm not taking them with respect to the continuous variable. So this means the partial with respect to the discrete variable X. I'm taking it there, and I get the following. I get the following result. I get lambda 1 through n plus a column vector of 1s. Sorry, missing a term here. Plus a matrix W. I'll define W in just a second. Times a column vector of 1s times lambda n plus 1. And this whole thing, I'm taking the inner product with respect to with F1 colon n. So if you look at this first equation, you'll see that I have an inner product in here, and the inner product is the product of this quantity with that quantity over there. So if I take, and then I get this equation for lambda n plus 1, which is the final one, which gives me the gradient with respect to x of phi of x n plus 1. And then I have the last equation, which says that the gradient with respect to capital U of the inner product of W inverse times lambda 1 colon n plus another column vector of 1s times lambda n plus 1 with F1 colon n. Now, if you look at these equations, let's just look at these for just a second, you'll see that by differentiating that Lagrangian with respect to all these variables, I get something that kind of looks like what I would have gotten had I used the calculus of variations and gotten the continuous time first order optimality conditions. You see that I have a gradient with respect to x, and it involves an inner product of lambda with f. And lambda transpose f we know is the Hamiltonian. Similarly, we get this thing that kind of looks like a transversality condition because we know that the final costate is equal to the gradient with respect to x, or partial of phi with respect to x evaluated at tau equals plus 1. So this kind of looks like the transversality condition. This term over here kind of looks like the first order optimality condition you get on the optimal control. Remember that dh du has to equal 0, and we get something in here that has a lambda transpose times f kind of behavior, and we're taking the gradient with respect to u. So the question is, how do we make this system look like the system that we got when we took the first order, when we applied the calculus of variations in and got those first order optimality conditions for the continuous problem? Well, the way we work it is as follows, is that in order to do this, we have to do the following thing. And there are a couple of steps involved in this, which is, suppose we define a new differentiation matrix. And I'm going to call this matrix D dagger, right? And D dagger has the following relationship to D, which is that D dagger is also of size n by n plus 1, right? The way D dagger arises is as follows, is that we assume that the costate is approximated as, so what I'm going to do is I'm going to take lambda of tau, and it's going to be approximated by capital lambda of tau, which is going to equal the sum from I equals 1 to n plus 1 of lambda I times Li dagger of tau. Now, what have I done here? I've taken a state approximation. You'll notice the state approximation uses points 1 to n plus 1. Well, we know that 1 to n are the Gauss points, and n plus 1 is the final point, right? So I'm still approximating this by a polynomial of degree n. The basis of Lagrange polynomials, Li dagger of tau, is equal to the product from j equals 1 to n plus 1. J is not equal to I. Tau minus tau j, all divided by tau I minus tau j. So it's a different basis of Lagrange polynomials. It still includes n plus 1 points, but it doesn't include the same points that were used as those that were used in the state approximation. We're using one different point. In the case of the In the case of the state, we were using the initial point plus the Gauss points. In the case of the costate, we're using the Gauss points plus the final point. So now what I can do is I can say lambda dot of tau is going to be approximated by this function capital lambda dot of tau, which is going to equal the sum from I equals 1 up to n plus 1 of lambda I Li dot of tau, Li dot dagger of tau. Now, if we look at this, I'm kind of running out of space here, but let's see if I can preserve. Nah, I can't really preserve any of this. I have to erase it. So now what we do is we see that this gives rise, if I just were looking at this gives rise to a new matrix, right? And that new matrix is going to be, suppose I take lambda dot and I approximate it at these points 1 to n plus 1, where j goes from 1 up to n, right? So I've got n plus 1 points in there, but I'm going to approximate this at the Gauss points, because again, everything is collocated at the Gauss points. What you get is, this gives a matrix D dagger. D dagger, right, is going to be a matrix that's going to be the coefficients. It's going to be Li dagger dot of tau j, right? These are going to be the coefficients in this matrix, where I goes from 1 up to n, and j goes from 1 up to n plus 1. Actually, sorry, backwards. I goes from 1 to n plus 1, and j goes from 1 to n, okay? Because I'm evaluating at the n Gauss points. Now, if I use that, suppose and now we can actually show, and this is kind of beyond the scope of what I'm trying to do here, that D dagger 1 through n, so that means columns 1 through n of D dagger, are related to columns 1 through n of D through the following relationship, where W is a diagonal matrix that contain the LG weights. All right? So if we now substitute that in, we could actually do the following. In the equations that I just erased from the board, we could actually substitute this whole thing in, because what we can do is we can actually get an equation for D1 through n transpose. If I take D1 through n transpose, I get minus W times D1 colon n dagger times W inverse, right? That's what I get when I'm all done. So if I substitute that in to the equations that I had up on the board earlier, which are now gone, unfortunately, so I can't refer to them except for on my note sheet here, what we get is the following. Let's go back and let's rewrite them, because I want to make sure that everybody can see this for a second time. So I'll grab these equations, which I have as follows. Let's see here. So remember what I had D1 colon n transpose times lambda 1 colon n is equal to the gradient with respect to x of the inner product of lambda 1 colon n plus W times 1 of lambda n plus 1 with f n plus 1. That was the first equation. The second equation I had was lambda n plus 1 is equal to the gradient with respect to x of phi of x n plus 1. And then the last equation I had was 0 is equal to the gradient with respect to u of the inner product of W inverse times lambda 1 colon n plus 1 times lambda n plus 1 f1 colon n. So those were the conditions I got, the first order optimality conditions of the NLP. Now I'm going to substitute into these equations the results from this relationship between the D matrix and the D dagger matrix. So we obtain the following. So if I take D1 colon n transpose, I can substitute it in from here, and I get minus W times D1 colon n dagger times W inverse times lambda 1 colon n is equal to the gradient with respect to x of the inner product of lambda 1 colon n plus W times 1 times lambda n plus 1, and then times f, sorry, this should be f 1 colon n, sorry, 1 colon n. That's the first equation. Now, if since this matrix W is not singular, I can do some manipulations here, and I can get that minus D 1 colon n dagger times W inverse times lambda 1 colon n is equal to, I multiply across by W inverse, and since W is a constant matrix, I get W inverse lambda 1 colon n plus, and then W inverse times W disappears, and I get lambda 1 colon n times f 1 colon n, right? Now, if you look at that equation, you'll see that, well, suppose now that we make the following substitutions. Because I've got here, if you look at this here, you'll see that this equation looks a lot like a derivative of a costate is equal to, or negative a derivative of a costate is equal to the gradient of something that looks like a Lagrange multiplier with f. And we know that the continuous equation is that lambda dot is equal to minus dh dx, and h is equal to lambda transpose f. So if I make the following substitutions, I should be able to make a relationship that actually makes all this kind of work out in a very sort of systematic way. This is n plus 1. My apologies. Which is as follows. Suppose we let the following things be true. Suppose I let the costate at the Gauss points, this is the costate at 1 to n, equal W inverse times lambda n plus 1 plus 1 times lambda n plus 1. So I'm basically making the substitution on this whole quantity right here, right? So then what happens is that gives me that W inverse of lambda n plus 1. What am I doing here? This is, sorry, 1 colon n. My apologies. 1 colon n is equal to lambda 1 colon n minus 1 times lambda n plus 1. So now if we take that and we substitute it in, we get the following result. So let's suppose I just substitute that whole thing in. What I get is, you get minus D 1 colon n dagger. And now if I substitute in W inverse times lambda of 1 colon n, what do I get? I get little lambda 1 colon n minus 1 times lambda n plus 1. And that has to equal the gradient with respect to capital X of lambda 1 colon n with f of 1 colon n. Now, I'm not quite there yet, but I'm almost there, which is that we know that D dagger is a differentiation matrix for the space of polynomials of degree at most n, right? Because it was a differentiation matrix for any polynomial of degree n. So suppose I substitute in a constant into this. I know that D dagger times a constant, 1, has to equal 0. So if D dagger, and we know that because of that, that d dagger is equal to d1 colon n dagger dn plus 1 dagger times 1. And that has to equal 0. So what this tells me is it tells me that d1 colon n dagger, right? If I take the if I sum this, right? Because I'm gonna take a linear combination of all the columns of this. This is the sum of d dagger of I equals 1 up to n, has to plus d n plus 1 dagger has to equal 0, which says that d n plus 1 dagger has to equal minus the sum from I equals 1 up to n of di dagger. So now I can use that fact in the result that I just obtained down here in that last equation over there, and I can simplify that result as follows, which is that if I take this result and I put it in over there, what do I get? I get minus d1 colon n dagger times lambda 1 colon n. And now I've got d1 colon n dagger times 1. But d1 colon n dagger times 1 is equal to minus dn plus 1. So I get here, I get minus dn plus 1 dagger times lambda n plus 1 has to equal the gradient with respect to x of the inner product of lambda 1 colon n times f1 colon n. Now, you can see that this looks like the costate equation, because if I rearrange this, I can rearrange it to be the following. d1 colon n dagger times lambda 1 colon n plus dn plus 1 dagger times capital lambda n plus 1 equals minus the gradient with respect to x of the inner product of lambda at the Gauss points with f1 colon n. So this would work out if I defined this to be the final costate. So suppose we say let lambda n plus 1 equal lambda, little lambda n plus 1, where this is the costate estimate at the final point. Then what I would get is I would get d dagger times lambda, little lambda, 1 to n plus 1 is going to equal minus the gradient with respect to x of lambda 1 colon n f1 colon n. Now let's compare that to the costate equation. What is the costate, the continuous time costate equation? So this is an aside. In continuous time, we get the following result, which is lambda dot is equal to minus hx, which is equal to minus the gradient with respect to x of lambda of tau with f of x of tau and u of tau. Right? This is what we get. So if you look at this, you'll see that that looks almost exactly the same as what's up here, except for now what I'm doing is I'm doing it in discrete time. So this is a discrete representation of the costate equation. And now the last thing we need to do is we need to just write down the transformation of the optimal control condition. So the transformation of the optimal control condition is actually quite straightforward, because if you remember, in the NLP, we got the condition. I'm going to write the NLP condition again. The NLP condition was that 0 was equal to, sorry, this board isn't erasing. Let's erase this a little bit better. So the NLP condition was that 0 is equal to the gradient with respect to u of W inverse times lambda 1 colon n plus 1 times lambda n plus 1 with f 1 colon n. But this is equal to little lambda 1 colon n. So what this says is, it says that 0 is equal to the gradient with respect to u of lambda 1 colon n with f 1 colon n. And now again, let's go back to continuous time. So in continuous time, what we had was this. We had that dH du has to equal 0, which is the same thing as saying the gradient with respect to the control of lambda of tau with f of x of tau and u of tau has to equal 0. So if you look at this equation and you look at that equation, you'll see that they're exactly the same, with the exception that this is done in continuous time and that's done in discrete time. So what we have is we have the following relationship that tells us estimates for the costate at the Gauss points plus the final point, which is that the costate estimate is as follows. Lambda 1 through n, so this is the costate at the Gauss points, is equal to the inverse of the weight matrix times lambda 1 colon n, which is the KKT multipliers of the NLP, or the Lagrange multipliers of the NLP, plus 1 times lambda n plus 1. This gives me the costate estimate at the Gauss points. The costate estimate at the final point is just equal to the Lagrange multiplier associated with the quadrature equation. Because remember, I defined this to be the KKT multiplier associated with the quadrature equation. We only have one more thing that needs to be done in order to complete this picture, which is we still need an estimate for the costate at -1. Well, we know that the costate at -1, well, we can do it either way. We know the costate at +1 is equal to the costate at -1 plus the integral from -1 to +1 of the costate dynamics, right? Well, what are the costate dynamics? The costate dynamics are going to be minus the inner product of lambda of tau with f of x of tau, u of tau, and then d tau, right? If I integrate the costate dynamics from the endpoint backwards, right? That's the Hamiltonian. So what I can do is I can take this and I can look at the equation that I've got for the costate, for the costate dynamics approximation, and I can integrate it, right? So what I can do is I know that this is equal to lambda n plus 1, or it's estimated by lambda n plus 1. This is lambda 0, which is what I'm looking for. This is the thing I don't have. And then what I've got is I've got plus. Now when I approximate this by quadrature, right, I've got the sum from what? From I equals 1 up to n of wi, I could put a negative sign here, minus wi times the inner product of lambda I, oh, sorry, little lambda I with fi, right? Now, if I do that approximation, so this is going to equal this thing over here. So what you know is that this thing over here, so now if we go back to the earlier equation, what we get is, boards just disappear. We have the following equation in the costate dynamics, which were that d dagger times lambda 1 colon n plus 1 is equal to minus the gradient with respect to x of the inner product of lambda 1 colon n with f 1 colon n. So if I integrate this, if I do a Gauss quadrature approximation of this integral, what you get is you get the following result. We know that lambda 0 is equal to lambda n plus 1 plus W transpose, which is now this is a vector of weights, times D dagger times lambda 1 to n plus 1. So if I do this result, I get that lambda 0 is equal to lambda n plus 1 minus d0 dagger, d0 transpose times lambda 1 colon n. Now this comes from the fact that what I've done here is I know that d dagger and lambda, the product of d dagger with lambda 1 colon n plus 1 can be related back to the matrix D, and I can use the fact that d dagger and D are related through the relationship that I wrote down earlier, and I get this result right here. So the final costate estimate that I get is as follows. For the LG method is as follows. Is we have lambda 1 through n is equal to, well, let's start with the final costate. So lambda n plus 1 is equal to the KKT multiplier associated with the quadrature equation. Lambda 1 through n is equal to the inverse of the weight matrix times the KKT multipliers at the Gauss points plus 1 times lambda n plus 1, and lambda 0 is equal to lambda n plus 1. And actually, you could write it either way. We'll write it this way. We'll write it as capital lambda n plus 1. So on this side, we all have KKT multipliers, and on this side, we all have costate estimates. Minus d0 transpose times lambda 1 colon n. So if you solve the NLP, so now let's go back for a minute to what we're doing here. We solved this NLP. The NLP was the NLP I wrote down at the beginning of the lecture. That NLP has the Lagrange multipliers associated with it. Some of those Lagrange multipliers are associated with the collocation equations. Some of them are associated with the quadrature equation. The Lagrange multiplier, which I'm defining as capital lambda n plus 1, is the one associated with the quadrature equation. And according to the Gauss method and this transformation, it says that the final costate, or the costate estimate at the final point, is simply equal to the Lagrange multiplier associated with the quadrature equation. As far as the Gauss points are concerned, now once you have that, you can get the Lagrange multipliers at the collocation equations by stripping them off of the solution to the NLP. They're going to be the dual solution to the NLP. And then you can estimate the costate at the n Gauss points by relating it to the Lagrange multipliers at the n Gauss points plus the final point. And then lastly, you can get the initial costate by simply doing a linear combination of all the Lagrange multipliers that you computed previous to that at the final point plus the Lagrange multipliers at the n Gauss points. And so this is the costate estimate for the Legendre-Gauss method, or also known as the Gauss pseudospectral method. And next time what we'll do is we'll do Lobato and we'll do Radau, and then what I'll do is I'll show you some results that actually give you some ideas as to how accurate some of these costate estimates are. And these are actually very easy to code up. Once you solve the NLP, you get a set of Lagrange multipliers, and the order of those Lagrange multipliers will be the same as the order of your constraints. So once you've solved the NLP, getting these multipliers and then doing these calculations to get the costate estimate is actually quite straightforward. It's just a simple matrix calculation. There's really nothing going on here. You can see that this is a linear transformation from one set of values to another set of values. So we'll do Lobato and Radau in the next classes, and that's where I'm going to stop right now. So.